let me not forget to turn the recording on this time, which I just did. So, all right. So we're going to start today with, as I like to say, our humanizing activity for the day. So let me just let me share the screen. Okay. Okay. So for today's activity, which can be captioned "Walking in Parks with Professor Ullman," this was actually this is a rather strange-looking shed that I found in a particular park called Woolsey Park. I was actually biking, not walking, but it caught my eye. I've never actually seen this park. I've passed it many times. I've never seen it up person, and I thought it's kind of interesting that they have like a glass shed with their police car in it. I assumed it was being used to patrol the neighborhood, but it turns out that if you look a little bit closer, what you'll see is that it's actually a smashed up police car. I wondered what that's all about. A little closer look. This is a police car from the New York, New Jersey Port Authority. And when you actually look at the memorial in the park, it turns out that this is actually a memorial to 9/11. So this is this piece that you can see here. This is a piece of the World Trade Center. I'm not sure exactly what the significance of this park is or what it's named after, but apparently they decided to create a park that was a 9/11 memorial. And what occurred to me is that, because we're living through this kind of unusual time, made me start thinking about, how unusual this actually is. So is this park near my house? Somewhat. I can bike to it. It's actually probably about a 7 or 8 mile bike ride from my house. And yes, apparently you're allowed, nobody report me, but I think you're allowed to go that far from your house if you're exercising. So anyway, anyway, it made me start thinking about what disasters I've actually lived through, disasters or crises. So I decided to catalog them all. So let's see, crises or disasters that I've lived through. 1, the Cold War. 2, Watergate, 1972, about. There was the seizure of the American embassy and holding of hostages for 444 days from 1979 to 1981. There was Chernobyl in 1986. The Loma Prieta earthquake in 1989. You have to go another 12 years to get to 9/11 in 2001. The conservative columnist George Will actually referred to. Sorry, didn't mean to turn the page, but he referred to the 1990s as our holiday from history. So it's kind of interesting that during the 1990s, very little bad actually happened. That was kind of an exceptional decade. There was the SARS epidemic in 2003. So that was actually, the SARS was a coronavirus. So you can think of that as kind of coronavirus, the prequel. Maybe, oh yes, that's right, World Trade Center 1993. That didn't make my cut, but yeah, that was on one of my earlier lists. I just wanted to tear it down a bit. You can think of the original SARS epidemic, since it was a coronavirus, you can think of that as kind of like Better Call Saul to the current epidemics, Breaking Bad. And there was the financial meltdown of 2007 and 2008. There was the swine flu epidemic of 2009. And then, of course, there's the election of Donald Trump, 2016. So as you can see, we've all been through some pretty awful stuff. And you know, if you keep some perspective, so that's 10. Somebody asked, that's very nice to say, don't be rude. I'm actually 50. So this is about one, if you think about this, this is on average one disaster every 5 years. So anyway, we will, I'm fairly confident we will, you know, obviously there are going to be some people who don't, and it's very sad, but I think that most of us will make it through this. So anyway, let's, okay, there's a little political counterpoint to my statement. That's fair. So, okay. That's true. I have made it through all of them. Okay, so let's go through, let's go back to math, as we always eventually have to. Let's see. Okay. So let me, all right, so let's do this graph sketching example. I'm just waiting for the comments just to see if there's, oh, I need to actually sharing that. And there we go. Okay. All right, so here we have a little more graph sketching to do. This is kind of a more complicated function than the one we did the other day. The reason it's complicated is that it has some asymptotes in it, so it has that little bit of complexity to it. Just recall that what we're doing with graph sketching is we're trying to use what we know about the shapes of graphs, the shapes of functions based on what their first and second derivatives are. Let me, in fact, just put those up. So recall that we have, this is going to be f prime is greater than 0 and f double prime is greater than 0 because we have concave up and increasing. Here we have increasing but concave down. And then here we have, this is going to be decreasing and concave up. And here we have decreasing and concave down. And we also recall that anytime that we can see a minimum, it's going to look sort of like that. So that's a minimum, which we can detect either through the first or second derivative tests. If we have a minimum, what we know is the function is decreasing to its left and increasing to its right. If we have a maximum, we have the opposite situation. So we have increasing to the left and decreasing to the right. We also know what I'm depicting here is really both the first and second derivative tests. If something is a minimum, not only we know that it's decreasing to the left and increasing to the right, but except in some very exceptional circumstances that we saw the other day, that means that the function is actually concave up at that point. And in the case of concave down, in the case of a maximum, we know that again, except in some very exceptional circumstances, not only do we have increasing to the left and decreasing to the right, but also we have concave down. So we know that we have here f prime is less than 0, f prime is greater than 0. Here we have f prime is greater than 0, f prime is less than 0. And we probably, not definitely, but probably have f prime prime is less than 0 and f prime prime is greater than 0. Recall that I had this really sort of weird example of f of x equals x to the fourth, where even though we have a minimum, we still have f prime prime equals 0 at that point. So anyway, these were the shapes that we were using to draw the graphs. So I'm just going to do another one of these. All right, so here we have function x squared over x squared minus 1. Can pigs swim? Did I put that in there? Oh, yeah, we'll get to that. Don't worry. Can't they? Well, you'll have to wait and find out. So I'm waiting to see what everyone says about the pigs. Nobody wants to hear about graph sketching. They just want to hear about pigs. So, okay. So because these derivatives, this is one of the issues I had alluded to the other day, that sometimes I'll just give you the first and second derivatives so that you don't have to calculate them. These are certainly something you would know how to do, but they're kind of messy. So I've just given them to you. So let's, as you recall, you have to get to a lot of, you have to use a lot of paper to do these. So let's, first of all, we're given f prime and f prime prime, so we don't have to do step 1 to calculate them. So let's find the transition points. We find the transition points. What we want to do is, first of all, find where f prime of x, recall that f prime of x equals, this is from the previous page, I'll just write the derivative, x squared minus 1 squared. What we want to do is find where f prime is equal to 0 or f prime does not exist. So first of all, f prime of x equals 0 when x equals 0. That's clearly going to be true because we have here, we have I'm not sure why the pointer is not working, but you can see that we have negative 2x in the numerator. So if I said x equal to 0, I'm just going to get 0 over, we'll end up with 0 over 1. So that's 0. Note that f prime of x does not exist where x equals plus or minus 1. Now, the question is are plus and minus 1, are they critical numbers of this function? I'm getting some answers here. Okay, so certainly it looks like they should be, and I'm sort of trying to lead you to that point, but it's actually, they're not. Now, why are they not? Why are they not critical numbers? Example of graphs. There we go. Take a look at the original function. The original function is, I'll point to it with this. The original function has the same denominator. So although it's true that f prime is undefined at plus and minus 1, so is the original function. A number can't be a critical number of the function if it's not actually in the domain of the function. So you have to be a little bit careful of that. A critical number is a property of a number that you can actually plug into the original function. And since you can't do that, you can't plug in plus or minus 1 into the original function for the same reason that you can't plug it into the derivative. It's not actually a critical number. So it's not a transition point, but it is going to be an important point in the function. And we'll get to that in a minute. Okay. So, but plus and minus 1 are not critical numbers because they are not in the domain of f. Okay. So now let's look at where f prime prime is equal to 0. Just check something here. Okay, so f prime prime is equal to 0. So this never happens because f prime prime is equal to 6x squared plus 2 over x squared minus 1 cubed. So there's no point where this is 0. So this is never 0 because you can't make 6x squared equal to -2 because a square of a number is always either 0 or positive. So there's no way to make this 0. And then for the same reason, we would normally look for points where the function is where the second derivative is undefined, but that's just going to be plus and minus 1. And for the reasons we just covered, those are not really transition points of the function. We do want to keep in mind what plus and minus 1, the fact that plus and minus 1 gave division by 0, because if you look at, let's go back for a minute again. Again, if you look at the original function, if I plug in 1, what I'm going to get is 1 over 0, which is infinity, or it's going to be at least plus or minus infinity. So what this suggests is that plus and minus 1 are going to give us vertical asymptotes, if you remember how those were defined from back in chapter 2. So you want to keep them in mind as vertical asymptotes, but they're not going to be transition points in the true sense. So x equals plus and minus 1 are vertical asymptotes. Okay. So the only transition point is x equals 0. Okay. So next thing we want to do we want to check f prime and f prime prime at the transition points. So what I'm going to do is I'm going to draw this number line. I'm going to put in 0, -1, and 1. So this is a transition point. This is going to be f undefined, and f is undefined. And now what I'm going to do is put in -2, 1, sorry, not 1, 2, 1/2, and -1/2. Why am I putting these in? I'll answer that question in a minute, by the way. Why am I putting these in the red points? The reason I'm putting in the red points is, as you recall, what we want to do is we want to check for the first derivative and second derivative being positive and negative by looking at points that appear in between the transitions. So since the only transition point is 1/2, and we have 1/2 and -1/2, sorry, the only transition point is 0, I would just want to check points arbitrarily on either side of 0. The reason I'm putting in 2 and -2 is that since the function is undefined at -1 and 1, really anything could happen across those points. So we want to check what's going on either side of that. Now let me answer Logan's question. What's the difference between a point of inflection and a transition point? The answer is that a transition point is a place where a point of inflection might occur. just the same as how a transition point is a place where a local min or max might occur. So transition point is just this kind of all-encompassing term that includes critical numbers and also includes places where the second derivative is either zero or undefined. So transition point really collects all the different types of transitions that might be happening at those points. We know that at critical numbers, we might be changing from increasing to decreasing or vice versa. That's what would give us a min or a max. At a point where the second derivative is either zero or undefined, we might be changing from concave up to concave down. So those are the types of transitions that we're talking about at transition points. And a critical number is one type of transition point. But the other type is where f prime prime is either zero or undefined. An inflection point is something that might occur at a second derivative type inflection point. Type transition point. Although it's not guaranteed to, as we saw. Just to draw it again, here we have a place. This was y equals x to the fourth, where we have f prime prime of 0 equals 0, but it turns out it's not actually a place where concavity is changing. So it's just a place where we want to look for where concavity changes. So that's what a transition point is. Okay. So, all right. So what I want to do is evaluate all of these. I want to evaluate f prime and f prime prime at all of these points. So f prime of -2, I've simply put in these values because I did them in advance. It's 4/9. F prime of, oops, I did not mean to do that. Second. Not sure why that happened. I must have hit something. Okay. So f prime of -1/2 equal to 16/9. F prime of 1/2 equals -16/9. And f prime of 2 equals -4/9. So f prime prime of -2 equals 26/27. And f prime prime of -1/2 is -224/27. F prime prime of 1/2 is also -224/27. And f prime prime of 2 is 26/27. Now, recall that we don't really care what these values are. What we care about is whether they're positive or negative. I calculated them, but we don't really need to know exactly what that is. So, I mean, we don't need to know exactly what they are, but I just wanted to show that they can be calculated. If you look at what's going on with the first derivative, what that means is that the function must be increasing here, which is a different color for that. It must be increasing at that point. It must be increasing there. It must be decreasing here and decreasing there. And the function must be concave up, concave down, and concave up. So this is how we're going to figure out what the graph looks like. So let's look at what we know about it. We know that f is increasing on the intervals if you look at with the points that I've used, were designed to represent certain intervals. So -2 represents the interval negative infinity to -1, and the -1/2 represents the interval from -1 to 0. So it's going to be increasing on the interval -1, negative infinity to -1, and -1 to 0. Say f is decreasing on 0, 1 and 1 infinity. Say if is concave up on negative infinity to -1 and 1 infinity, and f is concave down on, I want to say that it's on the intervals -1 to 0 and 0 to 1. But actually, if you plug in, just go back here. I'm telling you, these take a lot of paper, and if it looks disorganized, there's no way to do this otherwise. You look at the second derivative. If I plug in 0, what I'm going to get is 0 plus 2 over 0 minus -1 cubed. So I'm actually going to what I'm actually going to get is a negative number. I'm going to get 2 over -1. So that's negative. So I can actually include 0 as part of the concave down interval in this case. So we're going to say that it's concave down on the interval -1 to 1. And we can also say that f has a local max at x equals 0. Why? Because we already found that 0 is a critical number of f, and based on the argument I just made, we saw that f is concave down at x equals 0, or you could use the first derivative test and say it's increasing leading up into 0 and decreasing coming out of it. So we can say that f has a local max at 0. All right, now we should be ready to draw the graph. Oh, actually, we need to do asymptotic behavior. Or sorry, I'm just reading Maria's question. Let me answer that at the end after I show you what the graph looks like. Okay. Let me just consider the asymptotic behavior. So recall that f of x equals x squared over x squared minus 1. We can see is that to find the horizontal asymptotes, we know that the limit as x approach, we find the limit as x approaches infinity of x squared over x minus 1. Looking at the fact that the powers are the same in the numerator and denominator, we can just treat this. I don't want to go over the process of finding this limit at infinity. So that's going to be 1. And limit as x approaches negative infinity of x squared minus 1. That's also equal to 1. So we can say that y equals 1 is a horizontal asymptote. And we can also say that the limit as x approaches 1 from the plus side of x squared over x squared minus 1. If we substitute this, what we get is 1 squared over 1 squared minus 1 equals 1 over 0. We know that that's not an indeterminate form. That means that the limit is actually, when you get non-zero over 0, you're going to get one of the infinities. Approaching from the plus side, what we can see is that we're going to get a positive number on top, and once if we use, like, let's say 1.01 squared, that's going to be slightly greater than 1. So when I subtract 1 on the bottom, I'm going to get a positive number. So this limit is equal to positive infinity. That's enough to declare that x equals 1 is a vertical asymptote. And if I do the limit as x approaches -1 from the minus side, I only have to pick one side for each of these. That is going to be, for the same reason, I'm going to get -1. If I take -1.01 and I square it, I'm going to get something slightly bigger than 1. So that's also going to be positive infinity. So x equals -1 is also a vertical asymptote. Okay. So don't worry, I'm not forgetting about the question that's pending. I just want to finish the graph. So we're now actually ready to draw the graph based on what we already know. Let's put in. Okay, so there's x and y. What we know is that we know that y equals 1 is a horizontal asymptote. We know that x equals 1 and x equals -1 are vertical asymptotes. I think I said horizontal asymptote for y equals 1. If I did that, if I didn't, that's a mistake. That is a horizontal asymptote at y equals 1. Okay, now looking at the original function, what we can see is that f of 0 is equal to 0. So that's kind of a nice anchor point we can just put in there. Now, let me put in 1, 1, 0. Okay. Out of colors. Okay, so what we know is that f prime, it shows that the function is increasing on this interval. It's increasing on this interval, decreasing on this interval, and decreasing on that interval. We also know that the concavity is going to be, I'll put in what these stand for, because it's not really that I'm saying f prime is increasing. I'm saying that f prime tells us function is increasing. So this is going to be up, going to be down, going to be down, and this is going to be up. So we have a function that is increasing. We have a vertical asymptote. The function increases up to that point. Then it starts decreasing. And as you can see, it remains concave down in between the asymptotes. Now let's look to the right over here, to the right side of the function. We have a function that we know it's asymptotic to x equals 1. It's actually it's going to approach both the vertical and horizontal asymptotes. Then we know that it's decreasing, but it's also concave up. And we know that it's asymptotic to y equals 1. So it's going to look like that in that interval. And then here we have f is increasing and concave up. And we also know that it approaches y equals 1 as a horizontal asymptote on the left side. So we'll draw an increasing concave up function like that. And there you go. That's the graph of this function. I'm just waiting for a question. And I'll answer the other question that was pending. Is it possible to tell if the function crosses the horizontal asymptote? Yes, it does look kind of like a sad face. Okay, so let me just catalog the questions that we have pending. First of all, is it possible to tell the function crosses the horizontal asymptote like they do sometimes? And the answer is yes, and I'll show you in a second what that looks like. The other question was, is this a special case? Do you normally have to check for whether 0 is part of the concave down interval? I'm going to answer that question first. If a function is defined at a particular point, sorry, let me back up. We're checking normally for concave up, concave down, increasing and decreasing on open intervals. In other words, intervals that don't include their endpoints. If you notice the way that it's written in the textbook, that's the way the textbook always does this. And that's because the monotone function theorem and the definition of concavity. The monotone function theorem is the thing that tells us that a function is increasing when the derivative is positive and decreasing when it's negative. It actually only works on open intervals. So when we check for increasing and decreasing, we're doing it on open intervals. We're not including the endpoints of the intervals. That's it's the same for concave up and concave down. We can really only say it on open intervals. Now, in this case, the thing that was kind of weird was that there was a transition point at x equals 0. So I broke up the intervals like this. I broke up the intervals so it was negative infinity, negative 1, negative 1, 0, 0, 1, and 1 infinity, like that. Even though the function was actually defined at this point. So what I want to say is that where the function is defined, you do want to see if it is, you do want to check its value at that point and see if it should be sort of lumped in with the other intervals. So notice that at 0, I have concave down on the left, concave down on the right, and 0 is also a concave down point. So that's what would tell you you want to include it as part of that interval and not carve out the point in the middle. Here, of course, if you look at the first derivative, I have increasing to the left and decreasing to the right. So there I've got a positive derivative to the left and a negative derivative to the right, which tells you that as far as increasing and decreasing goes, 0 should not be included in either of those intervals and should just be treated as its own point. So yes, you do want to check any point where the function is actually defined and see whether it has the same properties as the intervals to the left and right. If so, you merge the intervals. Okay, good. Glad that makes sense. So I was just kind of making that up as I went along. Okay. So, ooh, David drew a very nice sad face with that function. Yes, that is, it is kind of a sad face sort of function. Yeah, that's okay. All right. Any other questions about graph sketching before we leave and go on to it? I think it's probably a more interesting topic. Horizontal asymptote. What was the question? Oh yeah, that's right. Sorry, that's right. I was going to answer that question. Okay. That's a very good point, because a lot of people forget that, it is possible to cross. That's not really even horizontal there. It is possible to cross a horizontal asymptote. Many people learn this in pre-calc, that an asymptote is a line that you never cross, but that's not true, because I can have something that looks like this. So let's think about what this actually looks like. If I have a situation where the asymptote is crossed, then that means that the function must have been increasing to get above the asymptote, and then it has to decrease toward the asymptote. So what that tells me is that I have, if it's, that means it's increasing up to some point and decreasing to another point. That tells me that this has to be a max, because the first derivative test tells me that that's what a maximum looks like. The next thing that has to happen is this function can't just keep decreasing forever. If it did, it would cross the asymptote again, and it wouldn't actually be an asymptote in that sense. So what this is telling me is that although the function remains decreasing here, at some point it must start decreasing at a lower rate, which means there must be some inflection point. The rate at which it's decreasing must itself be decreasing. Here it's decreasing a lot, and here it's decreasing a little. So that means that f prime itself must be increasing. In other words, here I've got, let's say, m equals -10, and here I've got m equals -1/2. Well, that itself means if f prime is increasing, that means that f prime prime is greater than 0, which means the function must have at some point switched from concave down to concave up, and that makes that an inflection point. So what we're looking for is a max and an inflection point to see if it crosses the asymptote. The other example of this opposite would be here I have a min, and again, there must be another inflection point. So that's what you're looking for to see when a function crosses its asymptote and then turns around. Does that answer the question? Okay, great. All right, so we're going to go now to the next topic. I promise we'll get to that pigs question that everybody wants to know about. So what we're talking about here, and this is section 4.7. This, by the way, is the last section that we do, because there's another section of chapter 4 that we no longer do in this class, and this is the last section of chapter 4 we do. Therefore, we're beginning the last section that you're going to be responsible for on the test that comes up later in April. So you'll have lots of time to ponder all these topics. So what we're talking about is applied optimization. The applied optimization is really when you take a word problem and you try to figure out how to get the most of something or the least of something. As you might guess, because we've already talked a lot about how to find the maximum value and the minimum value, what we're really going to do is take a word problem, translate it into algebra, and then use calculus to find to perform the optimization procedure on it that we've already covered. We're going to find the maxes, we're going to find the critical numbers, find, evaluate the function at its endpoints, and then use that to find the maximum and minimum values. Then there are some problems where we can't really say that the word problem describes a closed interval. That doesn't let us guarantee that there's a max and min, but at least we'll be able to say whether there is a max and min in those types of problems or not. So fundamentally, what this unit is about is reading the word problem and identifying the correct function and the correct domain. So essentially what you want to do as we do these problems is you want to identify the quantity to be optimized, trying to find the maximum volume of something, the maximum surface area, the maximum number of dollars you can earn. You're looking for that quantity. And then what you want to do is you want to be able to write that quantity as an objective function, as a function of some other variable in the problem. That function has a name, and it's called the objective function. In other words, this is the object of what you're trying to find the most or least of. You then want to identify the domain of the function, hoping that it comes out to a closed and bounded interval. Because if it does, what we know is that if it's on a closed and bounded interval like that, AB, then we know that we're guaranteed to have both an absolute max and an absolute min that we can find by the procedure that we already saw. So then you just simply perform the optimization procedure. If the domain is closed and bounded, then you have exactly this picture here where you're guaranteed to have a max and min that you can find fairly simply. If it's not closed and bounded, you might not get such a situation. You might get a situation that looks, let's say, like this, where if I have the interval 0 infinity, see there's no max, but there is a min. Or you might get the opposite situation. You might get something that looks like this. Or you could get even like this. You could get here. Here you have a local max, but it's not the actual max. And here you have an absolute min. So problems where the interval is not closed and bounded tend to be a little bit more complicated, but at least we'll be able to say there is a min, but there is no max, and we'll learn how to do that. So that's really what we're doing here. Okay. So let's do the first of these problems. This is the world famous farmer problem. And this is, of course, where we get to pigs. I know you're all waiting for pigs. So farmer has 120 feet of fence and wants to build a rectangular pig pen next to a river, and we're going to assume that pigs can't swim so that the farmer doesn't need to use any fence next to the river. Lydia is very excited about that we're going to get to the pigs. So question is, what dimensions, length and width, will produce the pen with the largest possible area? Because of course, you want your pigs to be able to roam around as much as they possibly can. That's actually not true. The pig would probably taste more juicy if you don't let it roam around that much. But if you want to be nice to the pig, it should at least live a good life. So you're going to let it roam around as much as possible. So here's the fenced area. And what we want to do is make that as large as possible. So the first thing we do is write out quantity be optimized. So that's going to be the area 10. And what we want to do is write the area as an objective function. And as a function, that's going to become the objective function. So write the area as a function of another variable. So the question is what variable we should use here. The way I see it is this. This is going to be a rectangular pen. So one side of the pen is going to be x. The other side is going to be the same value x. We might call this value y, except that we can know based on the problem exactly what y is, because y is equal, we know that we only have 120 feet of fence. So I have to subtract the amount of fence that I've already used, which is going to be one distance x there, another distance x there. So I have to subtract 2x. This is actually important. I cannot have two variables in the problem, although it would certainly be correct to say that area is equal to x times y. This is not a multivariable calculus course. When you get to Math 251, you'll be able to optimize a function of two variables. But until you get there, we don't have a procedure to deal with functions of more than one variable. So I can't really write it that way. And I have to get it down to, that doesn't sound fun. Actually, it's a lot of fun. But like anything else in calculus, once you know how to do it, it's fun. So anyway, we have to write the area as a function of x and y. So this is going to be, sorry, we have, sorry, I want to write the area as just a function of x. So the area, in fact, I'm going to make it clear that its area as a function of x is just going to be the length times width of the rectangle. So it's x times 120 minus 2x. That's true. Computer science majors can stop at Math 152 and they never have to get up to multivariable calculus. That is true. Okay. By the way, for people watching this weeks later on YouTube, the reason I'm responding to random comments is the YouTube version doesn't show the comments that we can all see here. So I'm not actually having a seizure. I'm responding to something. You just can't see what it actually is. So that's okay. I realized that when I watched some of the videos on, yeah, they're really missing out. When I watched some of the videos on YouTube, I said, oh, that's no fun. You can't see all the comments. It's much nicer when you can see the comments, but it doesn't seem that that you can do that. For the 2 weeks that these are up on Canvas, they deleted after 2 weeks. You can actually see the comments going live if you watch the video. Okay, so anyway, we have so a of x is equal to x times 120 minus 2x, except it's actually going to be more useful if I write this as 120x minus 2x squared, because I'll be able to find its derivative more easily. So let's see. Notifications. Okay. Okay, so it's 3. Let's find the domain of the function. Obviously, this is just a quadratic function which could be defined every place, but since this is part of a word problem, what I'm interested in is the feasible domain. So the if you notice, if you take a look at the picture here, there's sort of a limit. I can't have a rectangle that has I can't have a rectangle where the side is less than 0. There's no such thing as a rectangle with a negative length side. So x can't be less than 0. But it's also the case that x can't be greater than 60. Because if you think about it, if I make x 60, then I go 60 forward and 60 backwards, and I've used up all my fence. So I can't make x be like 100 because I run out of fence. So the most I can make x be is 60. So x can't be more than 60. So the domain is the closed interval 0 to 60. And that's, of course, really nice because I have a closed interval to optimize a of x on. So, correct, that's a closed interval. So, let's for optimize the objective function on its domain. So we have a of x is equal to 120x minus 2x squared. And the domain, just to remind us, is 0, 60. So a prime of x equal to 120 minus 4x. So we're going to set, clearly there are no places where that's undefined. That's just a linear function. It's going to be defined every place. So we set 120 minus 4x equal to 0. That gives us 120 equals 4x, or x equals 30. Just waiting for a question. Okay. So I'm getting questions about the 0 foot wide fence. It's not, so I'm not saying that we're actually going to build a pen of 0 area. What I'm saying is that if I imagine how long a rectangle could theoretically be, it could be 0 feet long, but it can't be -1 feet long. So that's why I'm considering the endpoints. If you want to say that really the feasible domain is that, that's fine. It's just that it makes it much easier for me to do the optimization procedure if I define it on a closed interval. So that's why I'm writing the endpoints as being included. So that's as you're going to see, you're never actually going to get an answer that's the endpoints in this case. So what we're going to do is we will plug in endpoints. So sorry, right here, 30 is a critical number. Plug in endpoints and critical numbers. So we're going to calculate a of 0, that's an endpoint, is 120 times 0 minus 2 times 0 squared, which is 0. So there's our pen of 0 0 0 area. The questions that are coming up, I'll answer them shortly. A of 30, a critical number, that's going to give us 120 times 30 minus 2 times 30 squared. And I calculated that already. That equals 3,600 minus 1,800 equals 1,800. And a of 60 gives us 120 times 60. Minus 2 times 60 squared. That equals 7,200 minus 7,200, which is 0. And as you expect, if we use up all the fence on either of the two dimensions, then we're just going to get a pen of 0 area again. So obviously, this is the maximum. So the value that gives us the max is x value that gives maximum a of x is 30. Keeping in mind that our pen is going to have x, and 120 minus 2x. That means that we're looking for a pen that is 30 by 60. So we should use a 30 by 60 pen. And that's the answer. I know many of you have actually seen this in pre-calc, but the way you did it in pre-calc was you plugged the function into a graphing calculator, or relied on the fact that a of x is quadratic and therefore its max or min occurs at its vertex, which is negative b over 2a. But this is sort of the calculus way to do this, which is useful because it works for things other than quadratic functions. So, let's see. Questions? What does the derivative tell us? Why do we take it? Okay. The question is why I use the derivative. The answer is, if you go back a couple of lectures, if I have any function and I want to find where its maxes and mins are, what I have to do is find its critical numbers. And then I can check all the critical numbers and the endpoints for maxes and mins. Now, why is that? That's because you look at this picture, if I have a continuous function on a closed interval a and b, the only places where a max or min could possibly occur is either at a critical number, so that's the absolute max, or at the endpoint, or at one of the endpoints. So here I've got f prime does not exist. Here I have f prime equals 0. Those are characteristics of the only places where a function can ever achieve its max or min, is either at the endpoints, or at a place where the derivative is undefined, or at a place where the derivative is 0, meaning the tangent is horizontal. So that's why we're doing this. We're just doing the same thing that we did back in section 4.2, except we have to create the function that we're performing it on in this case. So that's the answer. Did that answer your question, Andrew? What does A prime represent? Well, A prime is the well, A prime is the derivative of A. And what it represents, what its value represents, is how much the area is increasing or decreasing as I change the value of x. Like if you consider this, so a of x equals 120 minus 2x squared. So what this is really saying is that if this is x, the length of the pen, if I choose a length of the pen that has 0, that I choose a pen of 0 length, the total area is 0. As I increase the length of the pen, in other words, as I go from a pen that looks like this, where x equals 0, to one that looks like this, where maybe x equals 1 and the width is 118, where then here I have x equals 2 and the width is 116. I keep getting larger and larger pens until I get up to some point here at x equals 30, and then finally at x equals 60, I get down to a pen of 0. I get down to a pen of 0 width. So that's what A prime represents, the rate at which I'm increasing the width of the pen. Okay. So, all right. So we now get to the important question of can pigs swim? Because the presumption in this problem is that that I don't need to fence the water because the pig can't swim. It turns out that this is actually not true. Pigs can swim just fine. So this entire problem is completely contrived, all to make it so that you don't have to consider the fourth side. Because if the question is how much can you if the question is what is the optimal shape of 120 square feet of fence that where you form a rectangle on all four sides, the answer is just going to be a square. And that example is done in the book. So there we go. I suppose I'm not sure if all pigs can swim or if these are special pigs. I don't know, but I did find these out, and I was curious about that the first time I taught this example. Okay, so let's see. Do rectangle, which people unironically buy 30 watermelons. Yes, that is true. The most math problems are not intended to be no, most math problems are probably not intended to be realistic. Although somebody who I thought had relatively little sense of humor for a teacher once criticized a word problem that I have, saying, "Well, that would never happen. You know, there's nothing realistic in that problem." I said, "Oh, it's okay. The numbers came out just fine." So anyway, let's see. The rectangle inside is inscribed in a parabola. Let's find the dimensions of a rectangle of maximum area whose base is the x-axis, and that can be inscribed inside the parabola r minus x squared, where r is a positive number. So let's draw what we're talking about. So we're talking about really this parabola. This is y equals r minus x squared, where that's going to be the number r, the y-intercept. So if this is the case, then what we're trying to do is find the maximum area rectangle that I can draw like that. Now, what this means is, first of all, this is going to be, I'm going to say that the size of the rectangle is really going to be based on where I put this value, how far to the right I put this line, the right side line, because that's going to be the point x0. And because of the symmetry of the parabola, this is going to be the point negative x0. So this is going to be a rectangle that's completely defined by by where I choose the value x. Okay. So first of all, let's write this. Quantity be optimized is area. 2, write the objective function. In other words, I want to write area as some function. I want to write area as a function of something else. Notice that this point here is going to be x comma r minus x squared. So that gives me, the rectangle is going to have a height of r minus x squared, and it's going to have a width of 2x. Everyone see why? Okay. So the objective function that gives the area is a equals 2x r minus x squared. which is 2rx minus 2x cubed, which we know is going to be useful because we're going to want to take the derivative, so it's easier to write it in that form. So 3, choose the domain. We're guaranteeing in the problem that the base of the rectangle is down here. And for the same reason we discussed in the farmer problem, you can't have a negative height. And so the smallest you can possibly make the rectangle is just make it completely flat. So take a look at this point, because this is the furthest we can really go. This point is going to be where y is 0. So if y is 0, then I have 0 is equal to r minus x squared, which means that x is equal to the square root of r. So this point is going to be square root of r comma 0, like that. And what that means is that, and of course, I'm not going to want to put x to the left of the x-axis of the y-axis, because then I'd just kind of have this like flipped around rectangle. I'm going to assume that because the rectangle expands equally in both directions, that I'm just going to say that the minimum possible value of x is going to be 0. I'm just going to say it goes here and it expands to the right. So for the domain, I'm going to choose 0 square root of r. And now I'm going to optimize a of x on interval 0 root r. So we can see that a prime of x is equal to, looking at this form of the function, it's just going to equal 2r minus 6x squared. So that's clearly, there are no points where the derivative is not defined, so I can go a prime of x equals 0, implies that 2r minus 6x squared equals 0. That gives us 6x squared equals 2r, or x squared is 2r over 6, r over 3. So x is equal to plus or minus r over 3, but we can exclude the negative, because for reasons we've said, we're only going to consider positive values of x. So the critical number is the square root of r over 3. All right. So now we're just going to plug in the critical numbers and the endpoints. So we know that a of x equal to 2x r minus x squared. So a of 0, that's one of the endpoints, is 2 times 0 r minus 0 squared, which is 0, as we expect. If we choose x equals 0, we're just going to get a rectangle of no width. It's going to have no area. If I choose the other endpoint, that's going to be 2 times square root of r minus square root of r squared, which equals 2r, r minus r, which is again 0. Instead, I choose r over 3. I get 2 times the square root of r over 3 times r minus square root of r over 3 squared. So that equals 2 square root of r over 3 times r minus r over 3, which is going to be, this is going to equal 2r over 3. So that gives me 4r over 3 times the square root of r over 3. So that's clearly going to be greater than 0, so that's going to be the maximum value. So the maximum, the dimensions of the rectangle are, I have to go this amount in both directions. So it's going to be 2 square root of r over 3 by, recall that this dimension was r minus x squared. So that's going to be r minus r over 3, r minus r over 3. So that's going to be 2r over 3. So that's the size of the rectangle. Okay, that brings us to the end. We're going to do some more optimization problems when we convene next week. I guess you guys have a workshop pending. I'm going to post the next couple of sapling assignments, and that'll give you something to work on. Any questions before I leave? Okay, great. Yes, you too. All of you have a good week. Stay safe.